All right, so in this video, we are going to derive the D3 character table from scratch. And so the first thing we need to do when thinking about this is think about the different symmetry operations of this point group. We're in D3. This is very similar to D3H or D3D. It's going to be a chiral molecule because we don't have any mirror planes. So we got to think about what would be in a D3H type molecule or a D3D type molecule. D3H is very easy to visualize. That would be something like a triangle, just a totally flat triangle. Equilateral triangle would be D3H. Great equilateral triangle there. Um, Anyway, and so what we're going to have a principal rotation axis going through that triangle, right? That's going to be our C3. And then remember, the definition of D is that we have n perpendiculars C2s. And so for the case of D3, that means we're going to have 3 perpendiculars C2s. So if we list now all of our symmetry operations, let's walk through it. We're going to have identity. We always have identity. Use the hat notation to represent that this is an operation and not a class. And then we're going to have the C3 operation. That's a 120-degree rotation along what we define as the z-axis. We always call the principal rotation axis the highest order rotation that we have with the highest n, so C3n being higher than the C2s. So that's a 120-degree rotation, but we can also do a C3 2 times, right? That's a 240-degree rotation. That's a unique operation. We can't do a C3 3 times because that is just going to be equal to identity, right? That's a 360-degree rotation. We did 3 120-degree rotations in succession. So that's not a unique operation. So then our other ones, our only other operations in this point group are the 3 perpendicular C2s. And we can call those C2, C2 prime, and C2 double prime. And if we want, we can visualize these a little bit. Here's your C3 principal rotation axis. You can see in this cobalt complex, this is actually a fairly common point group for chiral molecules in transition medical chemistry. But you can see basically what's happening here is there's a triangle here, right, with these atoms. And so you're spinning across, those atoms are interchanging in the C3, and then also these back 3 atoms are interchanging. So that's sort of where this threefold symmetry comes from. And then because we're a D point group, we also have the n perpendicular C2s, and here they are there. You can see they're perpendicular to the C3, and there's 3 of them. These are 180-degree rotations. So definitely a little hard to visualize with the chiral molecules, but for deriving the character tables, you don't actually have to visualize them at all. Okay, I wouldn't even bother that. I would visualize a very easy point group like D3H, and then just say, well, I know D3 is going to have no mirror planes. So the next step is we're going to group these into classes. And, well, identity is always in a class by its own. Identity and inversion are always in a class by its own. Now I'm talking about classes. So I'm dropping the hat notation, which tells you that it's an operation. The 2 types of C3s, the C3 and the C3-2, those are going to go into their own class. They're both doing a very similar thing. And so we write that as 2C3. They're both doing rotations along the z-axis. And you can imagine that, on this triangle, if a C3 would interconvert these two, a C3-2 would interconvert this atom all the way to this atom. But if we just define things as rotating the opposite way, then what was a C3-2 would be doing a C3. And the reason why in the Dn point groups, these are not separate classes as they are in the Cn point groups, see my other videos on Cn point groups derivations, is because these C2s can be used to interconvert your 2 axis systems. So that's sort of where the math comes in. And it can be a little bit hard to know this a priori without really thinking about these different definitions of what classes are. So, for most cases, I wouldn't worry about it. You can look at the patterns of the character tables to sort of figure this out, or maybe, if you're doing this for a homework assignment, you'd be given some of this information about how the classes are grouped. Sort of depends, but you can come up with it using these definitions of, is there arbitrariness in the Cartesian coordinate systems being defined, and can you have is there a symmetry operation that allows you to interconvert between those Cartesian coordinate systems? And so same thing applies with these C2s. You can see that they're all pretty similar. And so the very hand-wavy way is just saying, well, those are all C2s. Those are all going to go in the same class. And indeed, when you have perpendicular C2s, except for the D2 point group and some other strange ones, they're going to usually go in the same class. So now we have our 6 operations in 3 classes. And so we are ready to create sort of the skeleton of our character table. So we always put, by convention, the point group of the character table in the top left. And we write the identity class first, O is in a class by itself. And then we have our principal rotation axis class. In this case, we have 2 C3s, the C3 and the C32. And then we have our 3 perpendicular C2s in their own class. And we can write some space here for evaluating what different Cartesian functions, linear or quadratic, might transform as. Because we have 3 classes, that tells us we're going to have 3 irreducible representations. This is one of our character table rules. You can see my character table rule video for more clarification of what these rules are. But basically, the number of columns has to equal the number of rows. So we have 3 rows and 3 columns. First irreducible representation is always the totally symmetric representation. What that means is we have 1s across the board. So that one's sort of your freebie. And then the next thing I always like to do is figure out these A and B values, these values underneath the identity class. We call this the dimensionality. And there's another character table rule, again, see the character table rule video, which states that the sum of the squares of the dimensionalities, so we don't know what A and B are right now, but we're trying to figure that out, is equal to the order of the point group, which is just equal to the total number of symmetry operations in the point group, which we already said is 6, right? 1 here, 2, and 3. And these characters underneath the identity, the dimensionality, they have to be 1, 2, 3, 4, or 5. And they're almost always 1, 2s, and 3s, okay? And so the only way to solve this, get something valid, is if you have one of these values be a 1 and the other value be a 2, because 1 squared plus 1 squared plus 2 squared equals 6. So now we can go in and erase our A's and B's after we figure that out and put a 1, 1, and a 2. All right, so our next step is to figure out what values we're going to have for the rest of our character table. And this is a pretty small character table. It's only a 3-dimensional space here. And so for these easy ones, I would just suggest using the orthogonality principle, another one of these character table rules from the video that I described before, to figure out what these values must be. And so what values will give orthogonality here? And so our first vector is using vector notation, 1, 1, 1, 1, that's gamma 1. And the dot product, I'll call this C and D, of 1, comma, C, comma, D, which we're trying to figure out, between these two vectors must be equal to 0. That's what the orthogonality principle tells us. All the different combinations of the dot products must be equal to 0. But there's an added complication here for these dot products. We have to normalize or adjust for the number of symmetry operations in each class. So under identities, all that means is we have to multiply by the number of operations in each class for each component of one of the vectors. So the identity has only one operation, the identity operation, in its class. the C3 class has 2 operations, so we have to multiply by 2. And the C2 class has 3 operations, so we have to multiply by 3. And so this simplifies now to just 1, 2, 1, 2, 3, dotted with 1 C, D equals 0. And so now we can think about what values would give us 0 overall. And whenever you have a dimensionality of 1, your characters here are only going to be 1s or -1s. So that really simplifies things. You're not going to have funky values like square roots, which you can have in some of the more complicated character tables that have values of 2 or zeros. Zeros are pretty common. Okay, so we're going to erase this here. And if we think about this, well, it has to be 1 and -1. And the reason is because, well, 1, and to write that out explicitly, just so we're on the same page of how dot products work, we're going to have 1 times, 1 times 1, the first components, plus 2 times 1, the second components, plus 3 times -1 equals 0. So we had to have a -1 here because it's worth kind of 3, and to cancel out the 2 positive ones here that were also worth 3, 1 and a 2. So that's a very fast way of figuring out, what these irreducible representations are. And we can actually do the exact same thing for the last irreducible representation. This orthogonality principle is very powerful. And remember, all 3 permutations must be orthogonal. So gamma 1 dotted with gamma 3 has to be orthogonal, gamma 1 dotted with gamma 2 has to be orthogonal, and gamma 2 dotted with gamma 3 has to be orthogonal. So let's think about gamma 1 dotted with gamma 3 equals 0. We have 1, comma 1, comma 1. Again, we have to multiply by the number of operations in each class. So effectively, this gets us 1, 2, 3, just like we had last time. Dotted with, again, we can use F and G here, maybe 2, comma F, comma G equals 0. And again, here you can stare at this for a while and figure this out. But the answer here that works, or the only answer that works here is actually 2, comma -1, comma 0. And the reason for that is if we have a -1 here, that it is worth 2, so it's a -2. It cancels out the 2 here in identity, so you get 0. And then you're already good, you're at 0, so you want to keep it at 0. So you better have a 0 as your C2 over there. And so at this point, we've sort of derived everything. We might want to just check that one more thing, which is that we have complete orthogonality, that all the vectors are orthogonal to one another. So let's check that gamma 2 dotted with gamma 3, we haven't done that combination yet, is orthogonal. So again, we're going to have our 1, gamma 2 is 1, comma 1, comma -1, and we have to adjust for the number of symmetry operations in each class, 1, 2, and 3. And then is that orthogonal with gamma 3, which is we just figured out was 2, comma -1, comma 0. I guess it's 1, 2, -3, dotted with 2, -1, and 0. And that equals 1 times 2 plus 2 times -1 plus -3 times 0, which indeed equals 0. This goes away, and these two terms cancel each other out. So we are good to go. And so the only last thing to do here in deriving this character table is get rid of our placeholder gamma 1, gamma 2, gamma 3. We didn't know what to call these yet because we didn't know what the values were. Now we have to apply the Mulliken symbol rules. And so I have a video on Mulliken symbols that you can look over if you don't know too much about this. But basically, if the dimensionality is 1, we're going to give it an A or a B. And so we're going to give this an A or a B. And the reason why we give it an A is because we're symmetric with the principal rotation axis. So actually, both of these are going to be A. Then to distinguish between them, because we have to give them different names, we can't call them both A's, that would be confusing. We just go to the next symmetry element, our only remaining symmetry class in this case, and we give it a 1 if it's symmetric, positive 1 there, and a 2 if it's anti-symmetric. And then if our dimensionality, our character under the identity, is 2, we give it a value of E. This E is the Mulliken symbol E. This E is the identity class E. So don't confuse these. But now we have our complete character table derived. So that's what we got here. We got this section of the character table. In the next video, what I'll do is I'll walk through how some of these different functions were derived, how you figure out that these different functions transform as they do, because we didn't actually need to use any of these to derive the character table. We just use our different character table rules. Sometimes it can be helpful, though, to understand how these functions transform and where this is all coming